Okay, we've got a moment and beam question here. It says the structure shown below is used to transport 500 kilogram containers. Well, there's the container, and you've got the beam supporting its weight and the reactions of R1 and R2 that support the beam at either end. The container's weight is distributed between R2 and R1, but we've got to work out how much of the weight is taken down R2 and how much is taken down R1. First thing, it says calculate the weight of the 500 kilogram container. Well, weight is a force, and force is a unit of newtons. Okay, we also know that the mass multiplied by the force of gravity gives you the force of the weight. So we've got gravity as a constant of 9.81. So the calculation we're looking for is that force is equal to mass times gravity, in which case we've got 5,000 kilograms times 9.81, and that's equal to 49,050 newtons. Okay, moving on. It says draw the free body diagram. Well, the free body diagram just shows, in terms of lines, all of the distances and forces. So there's a line representing the beam, there is a line representing the reaction R1, and there is a line representing the reaction R2. The other force that we've got here is the force of the container, which is in a downwards direction, and we know now that that is 49,050 newtons. The other thing that you've got to show in a free body diagram is the distances that the reactions and the forces are away from the what we call the fulcrum point. So there we've got 587 meters, and here we've got 127 meters, and that's the free body diagram. Okay, let's turn the page. It says calculate by taking the moments around R2 the size of reaction R1. Right, this is not as difficult as it sounds. What we do is we imagine R2 is now a pivot point, so it's something that everything can rotate around. Okay, so the weight of the container would react in this direction, and the weight of R1 would react in this direction, and this is the clockwise and anti-clockwise moments generated by these two forces. So it says taking moments around R2. Well, the first one we can write down is the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. Okay. We also know that a moment is a force times a distance. Okay. Now R1, which is this unknown, is 587 meters away from here. So R1 is equal to R1 times 587, is going to be equal to the container force multiplied the distance away from R2. So R1 times 587 is equal to 49,050 newtons multiplied by 127. So that's one side of the equation and that's the other. Now we want to get R1 on its own, so we need to transpose the formula. In order to do that, we simply divide both sides. by 587. These two cancel each other out, which leaves R1 on its own. So, quick sum now. 4, 9 and 50 times 127 divided by 587 equals 10,612 newtons. So we now know the value of R1 here, 10,612. It then says determine the reaction R2. Well, we know that the sum of the downward forces is equal to the sum of the upward forces. So all we need to do is subtract R1 from the container, and it should give us R2. So if R1 plus R2 is equal to 49,050, then R2 is equal to 49,050 minus 10,612. Minus 10,612 equals 38,438 newtons. Okay. Next, the container is moved using the mechanical system shown below, so you've really got to identify all the different mechanisms. Part A is the pinion, and part B is the rack. You really do need to know all of the different mechanisms to state the change in motion that this mechanism produces. Well, the pinion has rotational motion, whereas the rack has linear. So, rotational to linear.